Well, this is my last lecture. I will never give another lecture, and my last lecture will be given to the IRDG. Now, I want to take your minds, many of you I see are very, very much younger than me. One or two look a little bit older than me, but I won't point anywhere at them. I want you to take your minds back to when I was an undergraduate in 1954. I looked like that then. That's me down here. And then I want you to take your minds back another generation to when Harry Willis and Norman Shepherd were in fact undergraduates, and I looked like that. That's my mum, that's me. Right, so we're back now to just before the Second World War, and then I want you to take your minds back, if you can, 2 more generations back further to the beginning of the 20th century. And this is the real timeline that I want to just explore. Very briefly, let me get your laser printer, the laser pointer, so you really can see the thing. Right. 1880, really, it was the start of what led to the IRDG. The idea that in the infrared you could see group frequencies associating chemical groups with absorption frequencies. At that stage it was right up in the near infrared. But in 1900, Koblenz actually succeeded in running spectra from 112 organic compounds and produced an atlas showing the correlation between the functional groups and the spectra that he observed. By 1922, Hilger had come out with a commercial instrument, and it looked like this. This is a commercial infrared instrument, would you believe? And we'll go through this in a moment. We'll go see how it works. But as you can see, it stands up on a pillar. We'll come back to that in a little bit later. Now, if we go back to here, you'll see that by 1923, Schmeckel had predicted inelastic scattering, and in 1928, Raman actually observed the thing. I pointed out that unfortunately, poor old Mandelstam missed out, so it's Raman spectroscopy, not Mandelstam spectroscopy, but you know how it is. Right, now, okay, we go down here. What I want to do then is just stop for a moment at the Second World War, and let's have a look at what the equipment looked like and what people thought at that time. Now this is taken from a monograph by Sutherland. Now Sutherland's name may not be a name that you normally think of, but Sutherland was Norman Shepherd's, who of course died, Norman Shepherd's supervisor at Cambridge. Norman Shepherd, in turn, was one of his students was Don Powell, and Don Powell, who was a member of this august organisation, was my supervisor. So there was direct connection between. Now, here we've got an infrared spectrometer. What you've just seen, this is how it's actually laid out. So we start off with a source, and the source is the light picked up by a mirror, put through a sample here, it comes round and through a prism onto a mirror and then to a detector. You'll notice there's no choppers, no nothing. There's a slit here for the entrance and a slit for the exit. And by adjusting the angle of the mirror, you could scan from one wavelength to the other. Right, the big weakness in the whole thing was the detector. Here is from a 1920 catalogue from Hilger's, not even Hilger and Watts. It was Hilger then, and Hilger produced this pile of thermocouples. In a sense, that was quite a successful detector, except for one respect. It was very slow. It did, in fact, give very, very sensitive measurements, but they were very slow. There was no way you could chop the beam and use AC methods to amplify the signal. No, you had to use DC amplification. So how did they detect the output from these two terminals here and do so and using entirely DC techniques? Well, at that time, and it's almost gone out of use now, but not completely, there was, of course, the ordinary moving spot galvanometer. They do exist, but hardly at all now. The idea was a little coil here was such that the radiation, the signal came through the coil and then out, in this case, like that. And this was a pivot here, and here was a needle. This, in turn, was in a big, heavy magnetic field. Now, you could raise the performance of such a device by going to this. This is from 1900, but it hardly changed until the Second World War. The springs were replaced by a simple fibre, which was suspended here, and the whole thing actually hung in this magnet. Now, in order to sense what the angle was as you applied the potential across it, what you did was to put a light spot onto a tiny mirror, which was carried just here, and the light spot then jittered across a screen. Now here is a slightly later version, like very nearly new, 1939. Here's what it had grown to. Here's your mirror, and the actual coil is just down below here, the magnetic field being crossed here. And here is how you actually set it up in the lab. So you set it up like this. You applied your potential to the galvanometer, and the lamp here produced a beam onto there, onto a scale across here. In fact, people used to put it right across the lab and onto the wall. Thus, the dark in the dark arts of spectroscopy. Of course, it was all done in a dark room. Now, these instruments were reasonably good, but unbelievably slow. The trick was that this is for the infrared, you set the frequency, you set the wavelength, you then do two experiments. One, you let the whole instrument settle down, and you noted down on a piece of paper what figure you got off your scale. You then slid the sample in, and you watched the thing settle down again, and you got a new figure. I wrote that down, all by the way in the dark. You wrote it down. You then move the angle of the mirror, and you did exactly the same two experiments again, and on and on. It took several hours to scan a complete spectrum, but very often people were only interested in a small part of the spectrum, and they could then do it in a few minutes. Now, Harry Willis told me of his adventures during the Second World War. He was responsible, under Sutherland, of recording spectra of petrol samples pinched from the Germans. So you had a truck somewhere in the desert or something, or a plane would crash but it didn't go up in flames, and they recovered a bottle of the fuel. Now the fuel analysis was very important. Romanian oil was heavily aromatic, but the synthetic petrol that they made in the plants, the coal plants, the hydrogenation plants in Germany, of course, were very aliphatic, hardly any aromatic content at all. So by measuring and watching where the samples came from and how much aromatic content you had, you could tell information about how successful the bombing campaign had been and how the supply was working out for fuel, crucial to the Nazis' propagation of the war. And that information was based on infrared measurements made down in a dungeon in Cambridge at night. Harry used to say the big problem was that they worked for about 3 or 4 hours at a stretch. Why? Well, it was important that they didn't move. You had to sit on a stool and do everything carefully. Because if you moved, your radiation from your body was detected, and that, of course, upset the instrument. So you kept very still, and away you did. So I said, well, what happened if you'd been out on the night and you had a few beers? Oh, that was no problem. You brought a milk bottle with you. So in the almost complete darkness, watching this jittering spot, and of course this only worked at night when the buses and the lorries stopped running. This was how the whole thing was done. Now, at that stage, Raman was way in advance. Raman was just a far, far more practical technique than infrared. So in 1928, the technique was discovered. The Germans bundled in on it, and very rapidly during the 1930s, literally thousands of spectra were run by Raman spectroscopy. Why was it so easy? Well, the answer is we go back to here, kindly provided by the folks at Renshaw. This is a 1920s spectrograph. Now, this spectrograph, or things like it, or even much bigger ones and more modern ones than that, would be around before the Second World War in every well-established laboratory. Because spectrographic analysis of elements was absolutely routine at that time. Everybody was doing it. There was a set at my old college here in London, Sir John Cass College. We had an excellent spectrographic laboratory technique. What they did was they took a simple experiment between an arc between a pure carbon rod and the unknown. Let's say it was a piece of steel. You struck an arc, 200 volts DC, and you collected the light on a simple lens and passed it to the slit here. Went through a prism and produced a line spectrum across this plane here. In here, in this cassette here, you had a glass plate, the old-fashioned glass plates, and you could run it up and down. Oh, it doesn't run up and down anymore. Oh, yes, it does. Yep, here we go. So you would put it down there, and you had a little device here that you could just push in to cover this inside the slit, set everything up, and away you went for about a few seconds. You then would turn off, move up, do another one. You could do 10 or 12 spectra on one piece of glass. You then took it into the dark room again, and in the dark room you would then just develop the plate and you would get your spectrum straight away. This was routine. It was the standard method, instrumental method of doing elemental analysis. Steel industry, all of the metalliferous industries, and all sorts of other areas as well. Right, the Raman experiment fitted perfectly with that technology. You had a big mercury lamp, your sample in the middle, you almost always liquid, not exclusively so, but almost always liquid. The light was collected, which of course is an emission process, and passed it through such a device. Now when you did that, this is the sort of thing you saw. Right, now the top spectrum is the spectrum of the mercury lamp itself. No sample, this is the mercury lamp itself. If you look at the bottom here, this is what you get when you do a 1 minute exposure. A 1 minute exposure, you get these lines in carbon tetrachloride, and those of us who are Raman spectroscopists will be completely familiar with those 3 lines. Now, not only do you get the 3 lines, but they're very close to the line. They're at very low frequencies, which were very, very hard to do in the infrared at that time. So this was a far better technique. By the way, you've got the anti-Stokes line just about appearing there. Here's another one. This is a cyclohexane, and here you've got various bands here, all of the vibrational bands for cyclohexane that are at Raman active. So you can see that once you got cracking, you immediately ran Raman rather than infrared spectrum. You got the whole spectrum, you got it in a minute or two, it was easy. So why didn't it take off completely? And the answer was you had to purify all your samples. You had to purify them by double and even triple distilling, boiling the sample up with activated charcoal to get rid of any trace, the most minute trace of any fluorescence. If the material was even slightly fluorescent, then the fluorescence would have zapped completely the Raman spectrum. So we had a problem. At that time, the Second World War, in the middle of the Second World War, you could do infrared, very, very difficult to do, or but you could do it on almost anything. The alternative, you could run the Raman spectrum, but only on purified samples. So your sample of a bit of petrol that you picked up in the desert wasn't going to be very good for Raman. It would fluoresce like crazy, and there was no way you could triple distill it, because if you did, you removed probably a lot of the data that you wanted to get. So the answer was that Raman was wonderful in the academic environment, but not nearly so good in the ordinary applied area of the site. Now, the whole thing was changed during the Second World War, in that along came the attempts, and successful attempts, to make the first recording instrument. This is the Perkin-Elmer Model 12, the prototype. I picked this picture up, and this was the actual prototype without a cover on it. But it was a recording single beam instrument, and that was made possible because fast detectors were developed in the middle of the Second World War. The best ones were actually developed by a German scientist who worked at Hilger, named Schwarz. And the Schwarz thermopile was very, very popular once it was released for use in the civilian areas after the war. Now, it was developed as a fast infrared detector. It was developed for the possibility, only a possibility at the time, of guided missiles for use at the end of the Second World War. I believe they actually had the missiles, but they were never actually used in anger before the Second World War ended. So the detectors finished up in a very useful application, which was in infrared. They were fast enough that you could slowly chop the beam and then take the signal from the detector and amplify it electronically. And that was the breakthrough. That enabled it possibly. Now, Perkin-Elmer produced this instrument to a government contract during the Second World War, as did Beckman. They produced a rival, and the two American manufacturers did. Immediately after the war, other countries piled in, and we were in Britain very active indeed. Grubb, Parsons, and then of course Perkin-Elmer themselves, and so on. And then from my point of view, the whole story sort of finished and wound up and was all over when Perkin produced the infracore. This was a small instrument, only about this big, about that high, sat on the bench, fully automatic, 1950s, very cheap. It was only about £1,500 at that time. Mind you, that is a lot of money now, but it was £1,500 then, and it was almost mass-produced, and it swept through the whole of the community. Now, coming back to the Raman, of course, when you actually recorded your Raman spectra, and that's one of my interests, of course, you got this sort of thing. How on earth did you translate that into a meaningful spectrum? What about the frequency axis along this way? Well, that was a very easy thing to do, but difficultly easy if you know what I mean. You could always superimpose on any spectrum, such as this, you could produce an ion spectrum. Now remember, going back to the experiment originally done, was done here with your Raman source over here. With a mirror, you could arrange to use your two pieces of iron and strike an electric arc. Few seconds, you brought this through and produced a single spectrum on the plate, which was of the ion spectrum. Now the ion emission spectrum, right from the visible through to the UV, is very, very rich in lines. Strong ones and weak ones and so on. And they're well known. The position of those lines was completely well known even by 1900. So the result is you could, by a simple comparison, you could identify the wavelength of each of these lines. Now with your trusty calculator, you then simply worked out what the frequency... Yes, this is at 54361, and you worked that out, and then you did your reciprocal, and you did a bit of quick mental arithmetic. Oh yes, that line there must be around about 450 wave numbers. So you had to work in wave numbers in the Raman, and you had to do it by this simple but tedious method of calculation. Of course, when you got to the infrared spectroscopists persisted, especially in America, in using wavelength. So you had infrared spectra in wavelength, and Raman spectra were always in wave numbers. And it wasn't until really the 70s, before in the end the Americans decided that they would change over to wave numbers as well. For a long period, lots of instruments were available with appropriate accessories or modifications that the customer could easily apply, which enabled them to produce the spectra either in wave numbers or wavelengths. Now, that's really where I wanted to stop saying about the history. What I'd like to do, though, is to just reflect as a very long retired academic. When I was an undergraduate, I was taught, this is back in 1954 and 5, I was taught to do inorganic analysis. Let's start with that. The inorganic analysis was done by dissolving the sample up and then carrying out a series of precipitation routines to identify the actual material you got there. It took ages, and it was really quite tedious, but it worked. When it came to organic analysis, that was interesting. There was no instrumental input into the organic structural work that we were told about, and no instrumental input at all into the identification of organic materials in 1954-56. Why? Well, the methods worked. The way you worked for an organic material was you broke it down, you degraded the material, discovered that you thought you had a carbon ion. You then would, of course, make derivatives. Well, not done, I believe, these days anymore. A 2,4-dinitrophenylhydrazine was added, and you made your 2,4-dinitrophenylhydrazone. You then measured its melting point and consulted the wonderful works of Beilstein's Handbuch der Chemie, and that would give you hundreds of these melting points. If you got the 3 or 4 derivatives and they all matched up with your melting point, you knew what you got. Now, I was accused at CAS of cheating by the organic staff and was really pulled over the coals. In the spectroscopy lab, they had just acquired a Hilger H800 infrared. And even then, I was more interested in instrumentation than probably most people. And I was befriended by the man who later became my supervisor, Don Powell. So Don showed me how to use the instrument, and I was given an analysis to do in the 3rd year. So I quickly nipped down to the spectroscopy lab and ran the infrared. Within about 25, 30 minutes, I knew what the material was. I then went to the stores, got the sample, ran an identical spectrum, that's it, done. So I thought, well, I'll bet they won't let me away with this. So what I did was to then go back to the organic teaching lab and do the whole routine of making all the derivatives, which was rather easy since I knew exactly what was there. I then wrote it all up and simply did not mention the fact that I'd done the infrared spectrum. Unfortunately, Tom Powell opened his mouth and happened to mention this in the common room. This was picked up in the organic people. They went mad, absolutely mad. And I was told, you can't use these instrumental methods. They're all dominated by bloody knob twiddlers. I said, oh, right. Now a question to finish what I'm saying. Answer this question yourself. Why didn't we go down to the spectroscopy laboratory and run a spectrographical analysis in order to identify the metals that were present in the compound? It was quick, fast and reliable once you were taught how to do it. Why didn't we go to the infrared lab and do exactly the same for the organic samples? The technology existed already. Why wasn't it applied? Now, obviously, the examiners agreed that it had to be done by classical methods, because that's what we were examined on in the 3rd year. But I still, to this day, cannot understand why students should be taught using the latest technologies. And I mean latest, because remember, you folks who just got through your PhDs and were taught 3 or 4 years ago the techniques that you're now using and the ones that you've learned in the last 3 years will still be using them in 25 years' time. What is the point of telling you how it was done 15 or 20 years ago? By the time you're my age, you'll be way, way, way out of date. But you'll be out of date halfway through the process. And so I think everybody should use the very latest technique available at that time when they are undergraduates. And thank you very much for listening to my last lecture, and I hope you enjoyed it. Yes, certainly.
Any questions? Please.
For some years until 1998, I worked for Kodak near Liverpool, and sometime towards I think the end of the 80s, we had a few months working in association with Eli Lilly. It was strange because this was pharmaceuticals. Now, I had some relation with our quality control laboratory, and we were supposed to follow the FDA-approved procedures. So your story rang a big bell in much more modern times. I remember I had to identify a sample of ethyl acetate. And it took hours and hours and hours following the drug procedure. I said, well, I can do this in a matter of seconds by Raman.
Can I just stop you then? I'll repeat the question,
yes,
because many of you at the back may not have heard it. The questioner has pointed out that in industry in the 1980s, he was working for Kodak and he was collaborating with Eli Lilly, who of course are a pharmaceutical manufacturer, and he was required to examine a sample of ethyl acetate and decide and prove that it was indeed ethyl acetate but using the methods that the pharmaceutical industry were required to do in order to satisfy the pharmaceutical regulators. And that was incredibly difficult and slow to do. He could do it in seconds by using infrared or Raman, and that was not then accepted. That situation still applies. If the original license was listed, say, 25 years ago, technology used will have been acceptable in 25 years ago, and you have to stick to it. Crazy, absolutely crazy.
Comment, Pat. You asked why old methods were being taught. Well, I have two things to say about that. One, from a long...
Would you like to stand up? And then
as a non-academic, I would say possibly that one reason that classical methods of analysis were being taught is exactly the same reason as is sometimes adduced as to why classical languages are still taught in schools, i.e. that's what academics teach. The other is with regard to availability of equipment. I remember well, at a time when just before they were trying to level the playing fields between the then polys and the universities, there was a meeting at which it was stated that the median age of instruments in poly labs, the median age was 15 years. There you are. That's speaking from the body of an instrument manufacturer.
just one aside on that. I was given or lent a couple of monographs, and I took one from Sutherland's. I showed you the picture that you saw. There's also accompanied by that was another one that was written by Tommy Thompson. Some of you will remember Tommy Thompson. He was well known again in the IRDG. And he wrote a book in 1938 on spectroscopy and the course that he taught at Cambridge in 1938. And it was unbelievable. It was based on information and techniques that were then at least 20 years old. And he didn't mention infrared or Raman in his spectroscopy course at all. Sutherland was much more progressive, and in his monograph of 1936, he did go through infrared and Raman, as well as the other forms of emission spectroscopy as well. But it's incidentally that it seems to me odd that even the great Tommy Thompson was not able to impart and give this information to his students. He was quite happy to go on here at the early IRDG meetings about it, and even claimed to be the inventor of infrared, I remember at one meeting. But he was not prepared to give this information to his poor students.
Any more questions?
I just mentioned that Christian Ingold in this university, just 100 metres away, was measuring all the Raman spectra of benzene and substituted benzenes in 1934, 5, 6, published a whole lot in a complete issue of the Journal of Chemical Society for 1 month, 100 and something pages of it. So it was all well known, what was possible by Raman, using one of these things down here that I think is now under the DNA museum.
Yes, I mean, Ingold, did a whole, there were many people in America as well. I would have thought there probably were 3,000 or 4,000 spectra available to researchers, perhaps even 10,000 by 1939 Raman spectra, but nothing like that number of infrared.
Any more questions? Final question.
On the photographic plate, how do you quantify the intensity?
Sorry, I couldn't.
On a photographic plate,
Yes.
how do you quantify the intensity? Explain how to calibrate it.
Right. Now, yes, you could do it. Now, what you did was you record the spectrum through a filter which fitted just in front of, almost in the plane of the slit here. The filter was graded as nominally 100% transmission in steps down to 0. And you would put that in front and you would move that across one after the other, and each time you do your spectrum one after the other, and from that you could get an intensity scale. Now, to calibrate it, you then would do the repeat process with the ion spectrum, and you could see the intensity of the lines go down, and you would then try to fit the two together. Now, Ian Beattie, Ian, can you remember what they used to do for infrared absorption spectra, or at that time? And there was with emission spectra like Raman, they did something else, didn't they? And I can't remember how it was done. You could put an emission cell into the beam, and you recorded that with again this filter, which enabled with a series of spectra one after the other, from the 0 to the 100%, you could match up the intensity of the lines, and that way you got a crude quantitative measure. But it was quite difficult to do. Yes?
Pat, since we were really interested in relative Raman intensities, we used to use a densitometer, which Snowhite hated.
Yeah, the densitometer, you could use that as well. They existed. They projected a little. You put the plate on a motorised stage, and you could then look at it through a viewer coming through, and you focus the light spot through onto a photocell, and from that you could run it across a band and actually record a spectrum that way. But I know there were pretty crude things, but I remember we had experience of it at Southampton. We did some work on a chap, one student called Chris Veer, did some rotational spectra using a plate. And the last time I used plates at all, and he took them up to Cass, who still had a spectrographic laboratory, and converted them into plots by using their densitometer that they still had.
It's chlorine, isn't it?
Yes, chlorine and bromine and one or two other things.